class didn't work, so hopefully this one does. All right, so yeah, okay, so the last homework assignment, I already posted that. That'll be due 2 weeks from today. And it's going to cover this stuff. So frame limit analysis, plastic torsion, axially loaded beam, and the axially loaded beam is what we're going to talk about today. Then coming up after that, after break, we'll continue to have some more lectures and then talk about the final project. So normally I don't do this, but since this is my last semester, I don't have to worry about setting a precedent. So the three of you that are here today, you'll get to have a say. Ever since I've taught this class, I have alternated final projects, more or less every other year. Not exactly, not perfectly, but the final project that has historically been assigned to this class and was developed by the professor who taught this class before me is based on finite element analysis. And it basically will take, starting with today's lecture, and then continuing into the last few lectures, beam buckling and beam foundation, like beam on elastic foundation with buckling. It would look at a beam on an elastic foundation with an axial load, so where you have to consider buckling behavior of that beam. So you'll be involving beam behavior matrices, Winkler foundation matrices, and then the buckling matrix, which we're going to develop next week. So it's a bit more of an involved finite element analysis because it's going to bring into play eigenvalues and eigenvectors, so you're going to have that sort of solution. It will involve a MATLAB solution. It's an interesting problem. It's one that's a little bit harder to wrap your mind around just because it's hard to imagine a practical application for it, but there are such things. They're just a little less common. But it's a good problem to investigate and analyze, to think about, just think critically about the problem and think about how to piece all of those components together and form them into a solution, right? The other final project that I have assigned in this class is not finite element analysis, so it would be more focused on some of the other topics that we've covered in this class, namely combined loading, right, and Moore's circle with stresses, and torsion. So you'd be thinking about, torsion, bending, shear, and axial forces, and it's focused on analyzing and then designing a bicycle crank arm. So I think students in the past have liked that because it seems like it's a little bit more relatable in the real world. So again, since this is my last semester and I don't have to worry about setting a precedent, I'm going to seek your input to see if you have a preference either way, because I'm going to be developing or finalizing the final project over break. So any thoughts on that? Finite element analysis of a beam on an elastic foundation with an axial load, which will involve eigensolutions, or bicycle crank arm project. I will say they're both somewhat involved, right? You can think of either one of them as a really long homework assignment. No preferences? You have a preference?
I kind of like the bicycle one.
The bicycle one?
But
all
also
right.
I wouldn't be upset if I had the finite element analysis one.
Fair enough.
Because it would force me to learn finite element analysis.
Even better.
Yeah.
Yeah. All right. Aspen, you have any inkling? All right, fair enough. All right, well, I will. I was sort of leaning towards the bicycle crank arm myself, just because that will have been a perfect split, 3 and 3, of how many times I've assigned each one. So it might end up being that one, but we'll find out in about a week and a half or whatever. week after next. So, all right. And then last week of classes, we've got the exam. And then with these lectures, it's most likely, unless we are spilling over time with these guys, this will probably just end up being meetings where we can talk about the final project and work through whatever issues you have with that as you go through it. In the past, those have often turned into short meetings. So, but as I mentioned previously, right, even though we're not having a final exam in this class, we are required to meet this week on Monday of finals week. So I do have a guest lecture lined up for you. So it's going to be a local prosthodontist, Dr. Sven Bone. He's going to come in and talk to you guys about what he is doing to really just kind of transform that practice and the whole field of prosthodontics into one that is informed by engineering. So it's yeah, like prosthetics for your mouth. Yeah, exactly.
I had no clue what it was at first.
Yeah.
These dinosaurs, maybe.
Okay, good. Thank you for asking so I can clarify that. Yeah, prosthetics for your mouth. So some people need, a complete set of, they call it a full arch. So top and bottom, both sets completely removed and then replaced, and it's a pretty intensive process. But he's been hiring engineers to work on developing a more refined and analytical approach to doing this. It's historically been treated more as an art than a science, and interestingly, surprisingly, there aren't, and this was shocking to me as an engineer, there are no industry standards for it. Like there are no, like we have codes that we have to abide by. There's no such thing in the world of prosthodontics. So he's trying to change that and move it into a more science-based or engineering-based practice. So it should be a great talk. He's going to come in and you never know, could lead to a job opportunity. So yeah, so anyway, that's what we're going to be doing that's what I have planned for Monday, December 11th.
My roommate's a dental assistant.
Yeah.
He gets Mondays off.
He does.
Are you opposed to other people coming?
No, not at all. He's welcome to come. Yeah. Yeah, feel free to invite friends that might be interested. Yeah, that would be great.
Is that also when we turn in, like, when we could do, like, a correction exam kind of thing?
Yes. Yeah, so thank you for reminding me, because I will post, I'll try to post today more details on that. But yeah, that would be a good time to submit those, and that might be when I have them, when I have you aim to submit them. So yeah. But yeah, so, and then, yeah, I hope everybody comes to that guest lecture. It should be a good one. Probably be some extra credit tied to just that experience. So, yeah. All right. Very good. So, any questions so far about, or yeah, any questions on homework that's due or anything like that?
So, on the second one where we use the pressure, can you turn that into like a cylindrical pressure vessel?
Okay, so thank you for asking about that. I will clarify. So yeah, you have your rectangular cross section, and you don't want to turn it into an equivalent cylinder. That's not the idea. What I'm looking for is basically just kind of take a simplified approach to figuring out what the internal forces are. So if you take a cut, right, and look up, you're going to have your material, right, is going to be opposing the internal pressures that are applied to this surface. So figure out what that net force is and then distribute it to the material that's resisting it to get the internal stresses, right, in these two walls. And then for these two walls, you would cut here, and look that way or the other way, right, and apply the same method. For the longitudinal stresses, right, that's just going to be whatever stresses are acting on the end surfaces. Those will be opposed by the material in the cross section, right? So, does that help clarify? Yeah. So it should be this is similar to how the hoop and longitudinal stress formulas were derived in mechanics of materials. At least when I taught the class, that's how I presented it, and I don't know if any of you took it from Dr. Madison, but that's how she presents it as well. So this is very similar to that approach, but I wanted to make sure that nobody was trying to go overboard with the rectangular cross section and try and get an exact stress result from a rectangular pressure vessel, because that is more complicated. You have to think about stress concentrations and things like that, and that's not the intent of this problem. So yeah, just kind of simplify it.
So, and we kind of assume like no stress in like the punching shear direction because it's thin.
Right, yeah, you don't have to worry about punching shear. Yeah, so, yeah.
So I guess no stress in the Y, basically, the way that's oriented.
What direction was the Y?
Vertically.
This is Y?
Yep.
Okay. Yeah, depending on where you're looking, right?
Yeah.
Here,
I
it
guess I
would be
was
Y,
looking on
there
the
it would
bottom
be Z.
at point C.
You're looking at point C?
Yeah.
Yeah, then that's correct. There would be no out of plane stress due to pressure. Yeah,
Gotcha.
yeah. You would.
That's just an assumption we can make with like thin wall.
Pressure vessels.
vessels.
Yeah, yeah, that would be one of the principal stresses, and it would be a zero, a value of zero. It's close enough. It's not going to be perfectly zero because the pressure differential between the two sides, but it's close enough to zero that compared to the other stresses that we can approximate it as zero
Okay.
for the purposes of this class.
Yeah.
Okay. Any other questions? Okay. So we'll wrap up the thoughts on the sandhill analogy related to plastic torsion, and then we'll get into axially loaded beams. And that's kind of a lengthy lecture, so we probably won't complete it today. That is going to be relevant to one of the homework problems in homework 10. So just keep that in mind. If you get started on that assignment over break, you might need to hold off on completing that problem until the Monday after break when we finish that lecture. So, all right, so we were just demonstrating how the sandhill analogy is valid because it checks out with our circular cross-section. And now we will go ahead and apply it to a non-circular shape. So we want to know what is the ultimate torque of a shaft that has a square cross-section, assuming that it's a solid section. Then, applying the sandhill analogy, we would end up with a pyramid with a rectangular, a square base in this case. And remember that the whole point behind the sandhill analogy is that the slope of that hill is going to be equal to the yield stress, right? Because then that means the entire cross section has reached that yield stress. So we have the yield stress equal to H divided by A over 2, just using geometry. So we can write H is equal to that yield stress times A over 2. So then, relating volume of a pyramid, bring that down here, we have 1/3 times the area of the base times the height is volume of a pyramid. So plugging in some dimensions there and other substitutions. We have 1/3 times a squared for the area of the base, and then for the height, we have the yield stress times a over 2 as defined above. So that's equal to 1/6 times lowercase a cubed times the shear stress at yield. So it follows then that 2 times the volume is 1/3 little a cubed times tau y, and 2 times the volume is equal to the ultimate torque. So there is your answer. And then the next page has a few sketches that show contour lines to represent the sandhill on various different shapes. And as you'll see on that page, this analogy can also be applied to cross sections that have holes or cutouts, right? So it doesn't have to be a solid shape underneath. The way you would treat that is think about piling the sand as though there were no voids in the shape, right? And then just horizontally scrape off what you would have had, or I guess that would be if there were voids within, right? So pile it off as though there was no void there, and then just horizontally scrape off what would have been there so that you would form a flat surface over the hole. And then the resulting volume would be half of the ultimate torque. If you had a cutout, then you would have, slightly different, right? You would just imagine pouring how that hill would form if you poured sand over the whole thing. So yeah, a little bit different if there's a cutout compared to an internal hole, but you get the idea there. Questions? All right. So that completes the sandhill analogy. I guess to complete that thought, I can sketch, this might be helpful. For this one here, if you wanted to look at a profile of that sandhill, it would look something like this. Right. My notes are all over the place here. There we go. All right. So now on to the last set of lecture notes, axially loaded beams. All right, so if we have a beam that is also expected to undergo axial loading, then we have to consider buckling. Normally with beams and other structures, we proceed with the elastic analysis by neglecting the deflected shape that results from the applied loads as far as how it changes the geometry and then how it would change equilibrium, right? But for the case of buckling, we can't do that. So that we use the deformed geometry in order to develop our solution for buckled shapes. So we have a transverse force capital F, applied at some point along the length of this simply supported beam, and then an axial force also applied. We would have reactions, all right, at the pin support, we would have a horizontal reaction equal to the axial load. In our vertical reactions, if we were to conduct the equilibrium equations, would be on the left end, it would be capital F times, in parentheses, L minus A divided by L. And on the right, it would be capital F times A over L. So we have two regions within this beam to develop equations for. All right, so the first region would be between the roller support and the applied load. So we'll look at region 1 first. We cut some point before the applied load, expose the internal forces. We would have something like that. All right, there would also be an internal shear as well. That would be equal in magnitude to the vertical reaction, but that's not going to be relevant to our moment equation. So we'll go ahead and sum moments about the cut. And we're after the internal moment. So we'll get an expression m of x minus the applied axial load times the deflection, right, which is also a function of x, minus F times quantity L minus A over L times x is equal to 0. So I'm putting these moments and displacement values as functions of x initially to remind you that they'll vary with x, but from this point on, I'm going to drop that function component just for the sake of simplicity. So we'll go ahead and divide through by EI, and we would get negative m over EI, excuse me, I'm dividing by negative EI to be exact. So we have negative m over EI plus P times lowercase v over EI is equal to negative F times L minus A over EIL times x. All right, so now we're going to define a term for convenience. And we're going to call it lowercase fancy m squared. So lowercase m squared is equal to P over EI. And we will recall from previous moment definitions that negative m over, that's capital M, right? Negative capital M over EI is equal to the second partial derivative of deflection with respect to x. All right, so we'll make some substitutions. Namely, we're going to substitute this here, and we're going to substitute this here. And so we get the second partial derivative of lowercase v with respect to x plus lowercase fancy m squared times lowercase v is equal to negative f over EI times L minus A over L times x. So the equation for deflection in region 1 is going to be the solution of this differential equation, right? And as you recall, differential equations can have general solutions and particular solutions, right? Remember that from your DiffyQ class? So this solution will have the form of a constant C1 times cosine of fancy mx plus constant C2 times sine of fancy mx minus f over p times the quantity L minus a over L times x. And this equation is applicable for x between 0 and the location of the applied transverse load, which is defined above in the figure as lowercase a. So the first two terms in this solution equation represent the general solution, and you'll notice that this part of the solution is based only on the axial load, not based on the transverse load. All right, and that comes from this lowercase m we defined in terms of p, all right? So there's nothing in here that's tied to f. This term is the particular solution. So it's based on both loads. And if the transverse load is equal to 0, then that component will be equal to 0. Okay, so that takes care of region 1. Now we'll apply the same approach to region 2 to obtain an equation for deflection there. So region 2, we're cutting between the applied load and the right end. Some moments about the cut. We have negative m of x plus p times v of x, lowercase v, plus fa over L times moment arm of L minus x is equal to 0. Making the same substitutions that we made before, we would have second derivative of lowercase v with respect to x plus lowercase m squared times lowercase v is equal to negative f over ei times quantity L minus x times a divided by L. All right, so it's slightly different from the region 1 equation. The solution gives us the deflection equation for region 2, which will be a constant we'll call C3 times cosine of lowercase mx plus constant C4 times sine of lowercase mx minus the particular solution, which is going to be capital F over P times, in parentheses, L minus X times A over L. And this solution is applicable for X between A and L. And so now we have two equations and four unknowns between those equations. The unknowns being the four constants, C1, 2, 3, and 4. So we're going to use boundary conditions to solve for those constants in terms of the applied loading and the associated geometry. All right, so our boundary conditions, what do we have to start with? You can look at the whole beam.
Deflection is 0 at x equals 0.
Yep, you can start there. That's a good one to start with. So at x equals 0, the deflection in region 1, say of x, is equal to 0. So that would lead us to a constant C1 of 0. And then the other support, right, can give us another easy boundary condition to work with, which is if we plug in x equals L to the region 2 equation, we should get 0. So that will give us constant C3 is equal to negative C4 times sine of lowercase ml divided by cosine of lowercase ml. So we're making progress. Now we need two more boundary conditions. What can we use?
At x equals a, deflection equals f, or deflection force equals f.
You're on the right track. So at x equals a, that is definitely where we want to look. We can use continuity at that location, right? So we have two equations, one for region 1 and one for region 2. We know that if we plug in a to both of those, we should get the same result, right? So we'll do that for both deflection and slope because we're going to have continuity in both of those regards. So say at x equals a, deflection in region 1 should equal deflection in region 2. So from that, we'll find that C2 is equal to C4 times, say in brackets, 1 minus sine of lowercase ml cosine of lowercase ml divided by, that's sine of ml times cosine of ma, not ml, ma. And then in the denominator, we will have cosine of ml and sine of ma. All right, so far we have C1 is 0, we have C3 in terms of C4, and C2 also in terms of C4. So then our last boundary condition will complete the puzzle. So that's going to be at x equals a, the slope in region 1 is equal to the slope in region 2. So from that, we will find constant C4 is equal to negative in brackets cosine of ml times sine of ma divided by sine of ml, and that gets multiplied by f over mp, and those are all lowercase m's. So now that we know C4 in terms of ml, f, and p, we can go back and calculate C2 and C3 in terms of those values as well. So I can say so now we can solve, we can have all those constants in terms of the applied loads and geometry. And technically E and I, because that's built into the lowercase m, right? And so the total deflection for region 1 is shown here then, with all of those constants taken into account. So let's consider the placement of the transverse load at midspan. So I would put A equal to L over 2. And we'll call that location B. All right, and then that would mean that the deflection delta B is something that we can obtain from beam tables due to the transverse load. All right, so remember previously in this class I showed you those mechanics tables and we used them for superposition. That's what I'm talking about here. You can just find that center deflection due to a transverse point load on a simply supported beam. That would be equal to FL cubed over 48 EI. I'm going to say this is only due to the transverse load. It does not have anything to do with the axial load. All right, so deflected shape would look something like this, right, where this represents the maximum transverse displacement when A is equal to L over 2. All right, so now we want to figure out how much of that total deflection comes from just the axial load, right? We already figured out how much of it comes from the transverse load. And because we're still elastic, we can apply superposition, so we can treat them separately and linearly combine them like that. So for the deflection due to P, we can simply calculate the maximum deflection from the equation above, right? That would give us the total deflection, and then subtract our delta B, that's only from the transverse load. And this will use P equal to lowercase m squared over EI. And also, we will go ahead and use this formula and solve for f. So we'll substitute f is equal to delta b, let's see, times 48 EI over L cubed. All right, so we'll have maximum deflection at L over 2. Set that equal to the deflection in region 1 solved for using x equals L over 2. And that's going to be 48, making the substitution noted above, 48 times lowercase delta b over ml quantity cubed. And then in brackets, we would have sine squared of ml over 2 divided by sine of ml minus ml over 4. And those are all lowercase m's. So you can verify that algebra on your own, but this is what, I verified it myself before class, this is what this would reduce to if you plug in A equals L over 2, and also X equals L over 2. All right, so A represents the location of the transverse load, and X represents where we're calculating the deflection. So we can then say that the deflection due to the axial load is equal to 48 times lowercase delta b over ml cubed times that value in brackets minus delta b. If we divide both sides by delta b, we have 48 over ml cubed times that value in brackets minus 1. And remember, we previously defined m squared as being equal to p over EI from before. So we can plot this normalized deflection to find solutions. So we would find then that when ml is equal to pi, that represents the point where the axial load P has reached its first critical value. So in structures, we call that the critical buckling load. You two, Cash and Will, should have heard that before. You guys maybe, no? All right, so now you know. Critical buckling load. Now on the next page, I have that plotted, and we'll look at that in a moment. Well, we're almost out of time, so yeah, we definitely won't finish this lecture today. That's okay. All right, and then when m squared L squared, all right, if we square that, being equal to pi squared, that represents the first eigenvalue. So then plugging back our definition for lowercase m, that means P over EI times L squared is equal to pi squared. So that critical buckling load is going to be pi squared EI over L squared. And that represents what we call Euler buckling. So have you guys seen this derivation, or have you seen other methods of coming up with this value?
I just remember the equation.
Yeah.
I don't really remember how we got to it.
Yeah.
Fair enough.
Yeah.
Yeah.
We've definitely been shown something about getting to it, but I don't know. I don't recall it being this, yeah.
Like, I know my semester for eigenvalues and vectors and difficult was COVID.
Ah, okay.
So, yeah.
Fair enough. Well, I don't think, yeah, I don't know if they would have covered this application, but yeah, this is, now you've seen the mechanics behind your critical buckling load, right? So yeah, you guys, I expect you guys would recognize this equation for sure. But yeah, now you know how it's obtained using mechanics. So, all right, so on the next page we have the ML plotted against this normalized deflection, right? So you can see how as it approaches pi, right, that's where it's going to be the solution to the first critical load. And so if we want to generate our eigenvalue, eigenvector formulation, right, we want to omit the transverse force to obtain the true differential equation. And since we are out of time, I'm going to stop here, and that's where we will pick up on Monday. So just keep in mind when you go through, you might want to hold off on the last problem of homework 10 until we complete this lecture, all right?
And that homework's due the Friday after we get back?
That's right, yeah. So you'll still have plenty of time to wrap it up. Yeah. So, all right. Any questions, comments, concerns? Okay.
Last time I remember.
Oh.